Welcome to AP Podcast 17.2. This is on cell potential. Now we're going to look at some galvanic cells with some voltages generated. Now there's a couple terms here we need to revisit. Oxidizing agent, right? That pulls the electron. And remember, what happens to the oxidizing agent? It gets reduced, right? So if it gets reduced, that means it's accepting electrons, right? And the reducing agent pushes electrons, so it's getting oxidized. And so that means it is giving off electrons, right? So there you have it. Now, this push or pull that we get in a cell, the driving force, it's called the E of the cell. You might see the book put this in really small lowercase letters and this really fancy looking E. We'll sometimes refer to it as the EMF, and which stands for electromotive force. And the unit that we're going to use is a volt, and you're familiar with volts because you've been around batteries most of your life. But for our purposes, a volt is a joule of work per coulomb of charge. Now, what in the world is a coulomb of charge? Well, we're going to visit this a little bit longer. It's really the flow of electricity in amp seconds, and again, that brings another term. So we're not going to worry about it. For right now, we're just going to talk volts. We'll delve into that a little later. And how do we measure it? We measure it with a voltmeter, which probably makes sense to you. So let's look at a picture that's a much better representation of what I was trying to draw in the last podcast. Here's a piece of zinc. Now notice that the cells, pardon me, not the cells, that the electrons are flowing up, right? You see that right there? In order for an electron to leave, that means a zinc atom has to become ionized and become a zinc 2 ion, right? And so what's happening is this metal bar of zinc is slowly breaking down up here in the speaker. It's getting smaller and smaller and smaller. And then what's over here, as these electrons are flowing this way in, you've got the copper 2 sitting in solution, and the copper 2 is attracted to the fact that this piece of copper is becoming negative from the electrons, and so you're plating copper on that. And so this bar is getting a little bigger. And this is where copper plating and silver plating comes from. And you could put a very, very thin plate of metal on a key or silverware or whatever, just using this process. So it's a super useful process. Now, how does it look with a voltmeter? Well, there you go. You see a voltage up there. This is typically where we'll see. We don't have a unit there, but that would be volts. And we've got our anode here and our cathode. This funny looking thing right here, this is just a standard hydrogen electrode. And what this is this is a piece of platinum right here. And then they're pumping in hydrogen. And this is a second. All right, where was I? Okay. Anyways, this is a special electrode that is used when you don't have a metal bar. Like in this case, we might have, this is a zinc bar, and in the picture before it was there was a copper bar over here. But when you don't have a bar, they can use this, and it's a standard electrode. So you can imagine the conditions. You can see right here. 25 degrees Celsius, 1 atmosphere, 1 molar solutions. And the standard potential for that is, or pardon me, the electromotive, gotta slow down here. The electromotive force for that is 0. And so all the values that we're going to see on a reduction table is based on this electrode. So let's look at what we would do with some of these cells. So here we have a reaction that will generate a potential, and what we want to do is write out the half reaction. So you can see that zinc solid is going to zinc 2+. So if I were going to write the half reaction, it would look something like this. Zn goes to Zn 2+ plus 2 electrons, and then the other half would be copper 2+ plus 2 electrons. Yields copper solid. And so what we have there is our two half reactions, and now we can look up the table and find their potential. Now when we want to figure out the potential of this cell, and by potential I mean the voltage of this cell, I have to add up the potentials at each electrode, the one that's happening at the cathode and one that's happening at the anode. And so you can see this little equation at standard conditions right there. The potential for the cell is the zinc and the copper, and here the zinc is being oxidized and the copper is being reduced. Now, where do we get the numbers to be able to calculate this? Well, we just look at a reduction potentials table that looks like this. Look at those numbers. Now, this is right out of your textbook, and I will show you a couple examples of ones we're going to use. I hope this is coming out on the screen. It's pretty small, so I'll be writing a lot of stuff, but anyways, we'll just go from there. So we can look those up, and when we're going to calculate the E for the cell, there's a couple things we have to be aware of. One, when we add these two numbers up, we've got to make sure it's positive. You see that right there? It's got to be positive. Otherwise, the cell is not going to run. So it's got to give a positive voltage. And if you were to look at that reduction chart, you can see that in every case here, right, every single case, reduction is occurring. Well, in a redox reaction or with a galvanic cell, if you're having some reduction, you've got to have some oxidation. So even though these two events are occurring, we're going to have to flip one of the reactions to get to figure out the potential of the cell. Now, another important thing about that is this point right here. Potentials are not multiplied by the coefficients. Okay, this is going to be a little twist, because if you guys remember when we did Hess's law, when we did a lot of thermochem stuff, we always multiplied whether it's bond energy or the delta S or the delta G, we always multiplied those by the coefficients. In this case, we're not. Usually not a problem, but sometimes students forget that. So that's something we're going to focus on. So let's look at an example of how it would be done with this cell right here. Got it written out already. So here's let's determine the cell potential for the galvanic cell based on this reaction. All right. So I would look on my chart over here, and let's just pretend I don't have this written out. I'd look on the chart, and I would find I'm looking for copper getting oxidized, right? Now, is copper going to get oxidized? No, because these are reduction potentials. So I'm looking for copper getting oxidized. Well, actually, it's getting reduced, and I've got to flip it. So let's look over here somewhere. I got to find it here. Oh, here we go. Look at this. See it right there? There it is right there. 0.34. Now, notice there, copper is getting reduced, right? But in our reaction, copper is getting oxidized. So you can see right here that we're going to flip it. That's what we're doing right here. We're flipping that reaction. So if I look up on the chart, we saw this one right here at 0.34 volts. So here I'm going to flip it, right? And I change the sign. Super, super important. Change the sign, right? Okay. And then I'm looking for iron. Now it's going to be 0.77. Let me just show you where it would be over here. 0.77. So there's iron getting reduced, and there's the 0.77. So there's the two reactions, right? So I look there. Now I add up those two values. I add negative 0.34 and positive 0.77. What do I get? I get a positive 0.43 volts. Okay, so that's the potential of the cell right there. Not too bad, right? You just got to go look at a chart and that kind of thing. But it does get a little confusing. Now notice, if I was going to write out this reaction, look at the coefficients right here in front of the iron. You see these right here? Oops. And notice we did not multiply this voltage by that, right? Wasn't multiplied. We don't need to. I mean, those potentials, those reduction potentials are put there with that already in mind. Okay, so let's try another one. Here we've got a galvanic cell, and I've got aluminum being reduced, aluminum 3 being reduced, and magnesium being oxidized. So let's give the balanced cell reaction and calculate the E for the cell. Oh, now they want us to write the balanced cell reaction. Well, we can do that. So I'm going to use my chart. I'm going to find aluminum. Well, let's just find magnesium being let's find aluminum being reduced, right? That'll be there. So if I look at it, it's right there, and it's a negative 1.66. Okay, so let's go back to here. Okay, so I'm just going to write this out. Al3 plus. Oops. plus my 3 electrons, right, equals Al, and that was a negative 1.66. Okay, now let's get magnesium. Now look at right here; it's being oxidized, so we've got to flip that, right? So let's go back to our chart and let's find magnesium. And here it is, right here. There's magnesium being reduced. Okay, at a negative 2.37. Now, it's not being reduced here; it's being oxidized, right? So I've got to flip that. So I'm going to write Mg yields 2 electrons, and that is plus Mg 2 plus, and that was, now we flipped it, right? So it's like a negative of a minus 2.37, right? You guys with me on that? So now I've got to actually write out the whole cell. Now remember, when we balance redox reactions, not only do the atoms have to be charged, but the charge has to be charged. Whoa, sorry about that. The charge has to be balanced. And so we've got to make sure that we're going to balance everything. So if we think about these two things, what would I multiply this? I would multiply these by 3, right, to get 6 electrons. And I'd multiply these guys by 2 to get 6 electrons. And so the full reaction is 2Al. Oops, I'm going to erase that. That looks horrible. 2 aluminum, 3 plus 3 magnesium yields 2 aluminum plus 3 Mg2 plus. And when I add those two together, I get 0.71 volts. Okay? Not too bad, right? So that's really all there is to it. Now sometimes the problems will be a little more challenging. They won't give you this equation right here. They'll ask you to figure out who gets reduced and who gets oxidized without looking at the reaction. And that's not too challenging. You just have to look at this chart right here and figure out which combination of the two half reactions is going to give you a positive cell voltage. So there we have it. Hopefully this stuff made some sense. We'll practice this in class. See you next time.